talking about constraints and restrictions.
Okay, so last time at the end of the lecture, somebody asked me, like, where are we going with all this? Because we had done a loop calculation and cancelled infinities and so on. So there was a lot of tedious algebra. So overall, what we are doing is the following. We were doing the one loop, all orders in coupling, potential, which is also called Coleman-Weinberg. So this looks like if you have a interaction which is lambda phi to the 4, then you can have with 1, 2, n such vertices summed over all n, okay, 2 onwards. Okay. And this is what's called the Coleman-Weinberg potential. Okay. And for this, as I said, this is a thing that you are looking for now for the infrared physics. That means you are looking at large distances over which this potential extends. That means we are taking this background field to be constant over the entire universe and calculating the potential. So here, unlike the other loops where when you calculate the effective theory, the particles in the loops need not just be heavy particles, you have to include all the particles in the theory. Okay. And then I calculated this potential, one loop, and for this coupling I said that this looked like so this we did in detail, and it's a potential because the mass is phi dependent. So if you have V0, which is the classical potential, which is then this m square, just call it m square, will so I should give it another name. This is, let's call it m0 here. m0 square plus lambda by 2 pi square. So if you put this m square in this expression, then you get a potential in this field, and that's a Coleman-Weinberg. Okay. And next I'll tell you what happens when these things are in thermal equilibrium. So what happens to this potential at high temperature? Okay. So what I am trying to derive will be that in these potentials, what you will see is that you have terms of this kind. It will always look like that. It's a convex potential, which is, so at large phi, it will always increase. So all the terms are increasing in thing. So we are looking for something where a potential looks like as follows. Okay. So you started off here, okay, at the minima of the potential. So what you are plotting here is V phi versus phi. Okay. So here and this is phi. So at small phi, this will be phi square terms which will dominate, and at very large it will be phi to the 4 onwards, and intermediate, if you have something like a minus phi cube, then you have a barrier like this. Okay. And if you have a barrier, then what will happen is that at some point, okay, you will, this thing lowers and you will form a barrier, and there will be a tunneling from this place to that place. Okay. And if that happens, that's a phase transition. Now what does, so you will have a, this is called false vacuum, this is called true vacuum. That's a convention, phi t. So the field will move from false to true. The one which is higher is called the false vacuum, and the one which has a lower potential is called the true vacuum. So what does it look like in the real universe? The real universe, what happened was that you had a field value phi f everywhere. Okay, and maybe it was changing overall everywhere because of the expansion and the temperature. It was going down, but supposing it tunnels, then what happens is that not all the places in the universe are going to reach this place at the same time. Okay, so what will happen is you have the centers of nucleation, where this thing becomes phi t first. Okay. Now these will be what's called the nucleation center, and this will grow and so on. So then at some point these bubbles will overlap with each other, and then everywhere you will have phi t. So then you will have a phi t everywhere. So the universe will become a true vacuum everywhere. But you notice that there is a difference in the energy level between here and here. Okay, that is called the latent heat. So when your universe transferred from this place to that place, delta V, this delta V is called the latent heat. Okay, this has to go somewhere. So that will actually mostly be used to again reheat the universe a little bit, but a lot of that will go into production of so delta V or latent heat goes into production of okay. And the way it happens is that supposing you had these spherical bubbles and they expanded. Okay, it's a spherically symmetric system, so you write the Tij of this guy. It's a spherically, so it will depend upon R. And what? So bubble is that from here to here, supposing it reaches this place first. So here you will have a different value of the field density compared to the surrounding. But the whole universe has to become phi t. So this bubble will grow. And so similarly, if there is another place where this has happened here, so these bubbles will grow until they overlap, and then all field values become phi t. So this is how the phase transition happens, by bubble nucleation and bubble growth. And the reason you have bubble these points is because not everywhere in the universe this tunneling, this place is reached at the same time. Because there is a quantum process of tunneling which happens. Okay. Now, huh? Yeah, so this is what I am saying, that if you had a Tij for the spherical case and you write Hij, Tij squared, and then you calculate the dE by dt, the energy in gravitational waves, and multiplied by omega d cube k upon and so on. So this was my formula which I used, the master formula, that I take the stress tensor, multiply by this is the formula which this told me that if I have some Tij and I can find out the probability of emission of this Hij, this square, and then I have a phase space volume for the gravitational waves. Okay. Now if the bubbles did not collide, then you will see that the angular integral will actually give you 0. Okay. You need a quadrupole, you need a asymmetry for this to be non-zero. Okay. So that asymmetry will arise when you have this two bubbles colliding. Okay. So you have this situation. So you have collision of two bubbles. Then you have this Tij here and Tij here. There is a asymmetry. Inside is different from this. Okay. Then this angular integral of this Tij will not give you 0, and that collision of bubble will give you that asymmetry where you have a gravitational wave production. Huh? Phi t, but no, not everywhere is phi t. These two bubbles are phi t, and outside the bubble there is phi f. Inside, yes. Yeah, but there. So you have, let's say like that. Yeah, during the transition. Okay, so you look like that. So this is an asymmetric system. So anywhere where you have asymmetry, that this bubble collided with that bubble, then there is a asymmetry here. It is not a spherical symmetry. That front will give you a gravitational wave. Okay. All right. So, yeah.
So, suppose at a point the value of the field is 5.
Yeah.
Why actually propagating outwards like this?
So basically, what you will need is that this has to do with the pressure. That when you calculate the pressure, this has. When you try to minimize the pressure, you will see that the total overall pressure is minimized when this occupies the whole space. Okay. The potential, I'll just show you right now, is actually the free energy in thermodynamics, which is the pressure. So the pressure has to be minimized. So that will be minimized in the system where this occupies the whole space. Okay. And so that is why it will grow. The bubbles will always grow, because eventually you need a system where the whole universe is at this true vacuum. But asymmetry is created when this front and this front meet. So you have these two and there is false vacuum outside. So this collision creates an asymmetry. During that collision you will have a bubble. This. You have many fronts. So you sum over all fronts basically. So there is a summation over n, where n is each bubble nucleus. Okay. Angular integral? Yeah. Well, what you will see is that, you remember I had said that the coupling is Hij, lambda ij kl tkl. This was the actual coupling. Okay, the projection operator has a angular part. So this is a function of angles. So you can write down the functional form. Put it in this and do the angular integral there. Then you will see if it is a symmetric system, the whole thing will become 0. But if it's an asymmetric system, then this part will ensure that you get a non-zero. Okay. So overall, if you are coming from the particle physics side, the thing that you have to look for is, what happened to that? Yeah. This term. Because in the standard model, this term is very weak. So you don't have actually a strong first order transition, you have a very weak transition. So you have a transition where you have basically a crossover like that. Okay. So there is this height is not enough. So thermally, if this height is less than t, then it is possible that thermally it will cross over. Okay. It's not a quantum tunneling. So then it's what's called the second order or a crossover process. And in that case, you don't have this latent heat which is released, and you don't have any, this first order phase transition is also of interest for baryogenesis. So people have been looking for this first order transition even before the gravitational waves came up or became interesting. But now the main interest is that you have to show theories in which you have this barrier, and you have this hump, and you have a tunneling, and you have this first order phase transition which will release a lot of energy. Yeah, so the barrier height is very small. So the thermal excitation means that a field value somewhere, when a temperature fluctuation there will be a probability to get into the other side.
But would it depend on the time scale to take out the tunnel as compared to
Yeah, but here what happens is, if you have a tunneling process like that, you can carry, this tunneling is almost instantaneous. Okay, it's a quantum process. Right? Also, it is the energy difference which is relevant here. The energy difference here is very small. Okay? So the latent heat is the one which is the interesting question. There is a latent heat released here, and this happens much faster than a thermal process, which carries over slowly. Okay. So then,
this one you're talking about the QCD and the.
huh?
So this thing that barrier for standard is not about the QCD and the.
No, so this barrier you will see is coming from the gauge bosons. Yeah, QCD gauge boson. No, not QCD gauge. So let us talk about this H.
So in standard model.
Yeah, in standard model, what we are plotting is the Higgs potential. Okay, so you will have to plot things which couple to the Higgs, and you will see that the gauge boson W and Z will give you the thermal part of the W and Z, not this one. The thermal part of W and Z, I'll show you today, will give you a negative phi cube. Okay, but that coupling, so that will depend upon the gauge couplings. The gauge couplings are not enough. So for this standard model doesn't give you a first order phase transition. Okay. You had any question? Yeah.
We are using a real scalar.
Yeah.
If you use a complex scalar,
Ah.
then my potential will be a circle.
Yes.
You know it is a circle, then my phi t and phi t can differ, right?
So normally when you give a wave, see when you have a circle in the standard model, see the angular part is a Goldstone boson because it has zero mass, in the sense there is no potential for going around. So the mass of the Goldstone boson is zero, and that Goldstone boson appears as a longitudinal mode of W's and Z's. Okay, so that's the W and Z degree of freedom. Okay, whereas
What I was saying was that phi t, two different places go to the same phi t,
yeah.
they will have a different theta.
Why should they have a... So ultimately the only dynamical variable for which you are writing this thing is one real value. Theta is not coming in the equations at all. Theta is not a dynamical variable. So let us say you are talking about the mod of the H, which is... So theta actually appears as your gauge boson degree of freedom. Okay, so briefly then, okay, so here in the Coleman-Weinberg potential you have a mu. So briefly let me tell you what this mu means, and then I'll move on to calculations of these guys in. So which one? I'll erase this one. So in the standard renormalization, let's say you start with lambda phi to the 4th. Okay, so I am writing the coupling. So this coupling is lambda. Okay, and you add to this. So this is not the Coleman-Weinberg. This is and some cross diagrams. Something like this. So basically you interchange the legs in various ways, and this is your one loop corrections to this lambda, but this is proportional to lambda square. Okay. So what happens here is that here you have this L, which is lambda. So I'll write down the amplitude and I'll call it this one loop, and this one like we calculated last time. So this one will be, so I'll call it and I'll tell you why I'll call. And this CUV, remember this gamma plus 4 pi plus etc. Okay, you get something like this from these diagrams. Okay, so this part is what I'll call the renormalized diagrams, Lagrangian, in which I have a bare, I start with the tree level and I have a one loop. Okay, then I will put lambda. So I'll put a counter term. Okay, so I'll call it and the job of the counter term is, so sorry, yeah. So the job of the counter term will be that you just add terms which are minus of this ultraviolet, this part and this part. So this 1 by epsilon and this which we had, remember in the last this thing, you say that the counter term had that and we cancel that with the counter term. Okay. So in sum what we have is LR plus L counter term. So these are all together is what's called my bare Lagrangian. Okay, that I had a Lagrangian and I had a classical Lagrangian, I had a one loop correction and I had a counter term. All these together came is called the bare Lagrangian. That's a static Lagrangian. So what that, and this should be, this is of cutoff scale. Okay, so that is the basic assumption, that this is the Lagrangian got sent down. Okay, and how you broke up into this, into the renormalizal part and the cutoff part depends upon the mu you choose to do the experiment. Okay, so the overall L should be independent of mu, but each of these will be dependent upon mu. So this has to be dependent upon mu. Okay, and this Q is actually the momenta of these external particles. Okay, so all of them will be depending upon mu in such a way that the total Lagrangian has to be independent of mu. Okay, and then if you do this, so gamma 4 is basically okay. This has to be, the bare Lagrangian is independent of mu. This gives you that Okay. So the log of mu square is 2 times log of mu with a sign change, and this mu by d mu is just d by d log mu. So that will just knock off this entire term, and you are left with this coefficient with a factor of 2. That's this. Okay. So this is what you get. I think, yes. Sign is, this will be a minus sign. So basically this, you can solve this differential equation in mu, and what that gives you is that, so this comes from the fact that the bare Lagrangian has to be independent of the cutoff. Okay. So this gives you that mu lambda at mu r. So lambda r mu r, some scale. Okay, or the other way, let's. Okay, so lambda at any mu r, which is called lambda r, is related to lambda of the other mu by this relation. Okay, so here this is all, this is mu. So you can expand that. You can expand this assuming that mu is less, lambda is smaller than 1. So this tells you how mu changes. So coming back to our, so this is the renormalization of this coupling, okay, which comes from the fact that the bare Lagrangian does not change, but how you split the Lagrangian into the bare part and the counter term depends upon what mu you are using. That tells you that when you do an experiment, what coupling you will measure. That will depend upon what mu you are using. Okay. So the reason I bring it up here is that you have this potential, one loop. Okay. This is 0 because this is your full bare term with counter term and everything. So which means that lambda mu 5 to the 4 plus your m4 upon okay, this v. When you put it here, when lambda, you will get a change term coming from, so there is one, this has an important term, minus 3 by 2. This 3 by 2 will play a role in making this 0. That 3 by 2 is that 3 here, which is renormalizing lambda. So the crux of the matter is that this mu is arbitrary, and normally what we do for, in practice is use mu at the scale where the lambdas are known. So in the standard model we know that h is 2. This is the value of the field, and this is the wave at which we are measuring all the couplings and the masses. So the mu that we will use in practice for the standard model is that this is, we'll take mu to be v, and lambda v is the experimental measured coupling. Similarly, the top quark will play a role. The Yukawa of the top evaluated at v. So what you have here is this lambdas and couplings evaluated at v, And then this phi is a general arbitrary value of the Higgs field. Okay. And this relation holds, which tells you that when you change mu, the mu here changes, but so do the couplings in such a way that there is overall no change. So this is independent of the mu, although it is appearing explicitly in the formula. Okay, so that was the coupling, that was. Okay, so now I'll so what happens? You have these scalars in the theory. So you are looking for, so this is phi here, outside phi inside, that's a scalar. You could also have gauge bosons. So phi phi. So this can be W, Z in the loop, or you can have a top quark. Let's say this is the top and this is your Higgs field. And this is your Yukawa coupling. Okay. Now this diagram actually is the same as this bosonic diagram. If you, and I want, so let me have vector. No, this is a cup. So okay, this is still the one loop for the vector contribution. I'll put a V here. That will give me, that is the same formula, m square of the vector. There is a dependence of the vector on the background field. There is a different constant here when you do the calculation, and this, there is a overall factor of the number of vectors or degrees of freedom. So this is 3. Okay. So each vector is 3 degrees of freedom, 2 transverse and 1 log. So it's the same formula with the same story, and you just put the mass of the vectors here. This is mv, and the phi comes in the mass dependence of the vector. So let me write down, if you can. Okay, I'll give you the thing, the formula for the standard model in one place at the end. You'll see. Okay, next is fermions, and that is a little bit different. So let me have what happens, how do you draw the fermion loops? And then you'll see that the thermal thing is a very straightforward extension of this. I'll show you. So now we have to do a path integral of the fermions. Okay. So what you are looking for is so there is a Dirac fermion which has a coupling with the Higgs field. Okay. So the effective mass is psi bar psi. So the effective mass is m plus yt times phi. So there is a field dependence here, and you want to look for that formula with the dependence on this effective mass. Okay. So here again you have to do Here, in the scalar case, we split the field into a background plus a fluctuation. In fermions, there is no background because fermion occupation number is 0 and 1, so it does not have a classical background. So fermions is always a fluctuation. Okay. So what we have here is that we have to use e to the I gamma phi will be d psi bar d psi e to the this L. And this phi. So integrate out the fermions and you are left with whatever, that will leave the phi dependence. Okay. So we have to do the same path integral for fermions. And so let me quickly give you. So what happens here is that normally in canonical field theory, we treat these as anti-commuting variables, right? That is because we write them as operators and then we define anti-commuting operators. The operators have anti-commuting property, which means the fields have anti-commutation properties. But in this path integral, we are treating them like fields. Okay, we are not bringing in operators. So we have to treat them as numbers which are anti-commuting. So those are called Grassmann numbers. And very briefly, let me give you the property that we need for this, for calculating this thing. So let's have two Grassmann number, independent C and C bar, and they have the property that C square is 0, C star square is 0, okay, and C star anti-commute. That means C star is minus C. Okay. When you interchange, it changes sign. So that's the property of these numbers. Okay. Now, clearly, any general f of C can be written as A plus B C, where these are complex numbers. A and B are complex numbers and C is your Grassmann number. Okay. Because you have a quadratic part, it will be 0. Right? We want to introduce something called DCFC, the integral, and we want to have a property that this should be such that it should be shift symmetric, C plus eta. That means if you shift the integral by a variable, if you shift the coordinates, the integral does not change. If I want to have this property, I write this FC as this. On left hand side I write that, and on the right hand side I write this with a C plus eta, where this is also a Grassmann. Eta is a Grassmann number. Okay. And we want the two sides to be equal. So you will see that the only way the two sides will be equal will be if DC is 0, DC of C is 1. Okay. So integral DC FC is B. Okay. So these definitions are coming from the fact that you have to have a shift symmetric property of the integral. So you can see that intuitively integral of does the same thing as what you will expect from a derivative. That integral of a constant, so let us say this was B, some other thing, derivative of a constant is 0 and derivative of C to C is 1. So derivative and integral do the same thing in this. Okay. And same rule for C star. Okay. So now we are done. We can tell how to calculate this guy. So now you see that if I have DC star DC e to the power minus C star BC, okay, this will give me I expand the, yeah, it's a notation in the sense that this C star has to be treated independent of C and they have to anti-commute. So this C star has to have the same type of properties as your psi bar in your field theory. No, a complex conjugation of C is not C star in this case. This is independent. Yeah, whereas in the actual field, when you have a Dirac field, there is a relation between psi and psi bar, but here we are treating like independent. Yeah, it's sort of a dual, right. So here it was B, this is B, right. So this Gaussian integral actually instead of square root of 1 upon root B, like in the normal this thing, it will just be here. And so basically, so if I have a column of C, dci star, J, okay. So now I make a matrix out of it. I have a column of Ci and Cj and there is a matrix. Then this is determinant of B. So this is true also for operators. Same story. Okay. So this is what I'll use to calculate this guy. Yeah.
So
Yeah.
usually in Coleman-Weinberg, the original paper, for instance, they start with m square equal to 0 so that radiator correction can break.
Yes, yes. Yeah.
So in that case, I would have thought that it would be lambda square phi c square instead of your m square b phi square.
What do you mean? Lambda square?
Lambda square phi c square.
Oh, I'm so sorry. This is M4. Yeah.
So, and I think what you are working with is
So what?
phi square m square. There's the classical mass is the thing that you're putting here.
No. So this M. So let us say this was for the scalar theory, the same story.
Yeah.
My M. So I'll start with L is equal to half M square phi square plus lambda to the 4 factorial phi 4. And this thing M square is V double prime.
So it contains the m square plus lambda.
Yeah. So this is basically M square plus lambda by 2 phi square.
So
And this could be a minus M square like in the standard model 0. Right.
yeah. So, but if that is the case, I feel like okay, yeah, maybe. So if m square is 0, I remember very clearly. I'm almost sure that the constant there was 25 by 6.
The constant term is?
25 by 6, not 3 by 2.
Yes. So, okay, so there is a way that comes. Yeah, you're right. So what happens there is that you fix, so you write your constants in such a way, there is a different way of renormalizing it. Yeah, that's true. So what you do then is you renormalize in such a way that you say V prime of phi at the minima is 0. So, and the second thing you do is that V double prime of this thing phi is so what you
I think it's very lambda.
this is fourth thing is to lambda and V1 double prime at phi equal to 0 is 0.
So it's basically some sort of mass shell type of a thing.
Yeah, so this is a different renormalization gives you 25 by 6.
So you are renormalizing the equation in terms of mu. This would somehow be in terms of m.
Yes, right. So a different renormalization scheme will give you that 25 by 6. That's correct. Okay. So it depends upon how you measure lambda, your couplings. Here we are measuring lambda at the mu and that's what I am using here. Okay, so here, where was I? Here. So now I'll do this very quickly. I have to calculate, so I'll write it somewhere nicely. Yeah, here. e to the gamma is this. d4x del mu m effective. So m effective contains that Yukawa term also. Okay, and I'll call this m just to save. So this m is m0 plus yt phi, the bare mass plus the coming from the field Yukawa term. Okay, and this will give me determinant of this operator. Okay, and we just do it like last time. This is the determinant of the operator, and we write it as e to the power trace log okay.
Out of this, whenever you are writing this m as m0 plus yt5, you are always assuming that there is a scalar field which is connecting with the fermions.
So that is the purpose of this exercise, that the scalar field potential you are trying to find out after integrating out the fermion. So if there is a scalar field which has a Yukawa, then the fermion in the loop will contribute to the scalar field potential.
No, my question is it always, so I know for the standard model is fine, but in general is it,
So standard model, it is not true for neutrinos, for instance. There is no coupling with Higgs.
that's why I was,
So then you do not need to integrate out neutrinos.
I was sort of more general. Suppose you have some theory where you have fermions which are not coupling to phase.
Then you don't need to integrate out those things. You don't have to put them, because those integrating out those things will not give you anything in this one loop. Maybe in higher order you will give. They are coupling to something which is coupling to Higgs. But here you don't consider them. And for the standard model you don't consider neutrinos. Okay. So this, as I said last time, this goes the same way as the last time, except for the fact that we have a minus half here, because this is 1 by determinant of square root in the denominator, which gave you a minus half here. So there is a plus sign here. That's the only thing, with a factor of half missing. But that half will come from the following. And this trace means trace over the space time, and log, and like last time we have a complete set of states in which we calculate this. So this will be d4k upon, so this goes just like I did the scalar calculation last time. Okay, once at this point onwards, and this is log of, okay, so this I am going to write as square of this with a half. Okay, and the square of this is just, now it is p mu, and I go to this, k mu, and I go to the Euclidean space. This is all like the last, same thing which we did the last time, so I am not repeating. Okay, so I go to the Euclidean k where this I goes away. So I just have a, and there is a change. So this will give you k slash Euclidean plus m. Okay, there will be a minus sign here, minus sign, this will go away, and square here. So this will give you e to the power d4x, okay, d4k upon, okay, half, and there is still a trace of over the Dirac indices. Okay, so when you square it, there is still a trace of, this is the 4 by 4 Dirac indices. When this has become, so this will become a scalar and you will get this multiplied by a Dirac trace. So this will become basically, sorry, at this point I will write it like that, trace here, let's say, of k square, and this I will write as k square plus m square, trace of this 4 cross 4 matrices. Okay. So overall, the only difference is you got a different sign. You got this factor of half back like last time, but this is going to give you 4. Okay. So a fermion contribution will be exactly the same so if I just calculate fermion, one loop for fermions, okay, so this will be inside what is there d4x, this guy, d4k upon 2 pi to the 4, okay, I have half times 4 times k square plus m square, where k square is k0 square plus vector k square. This is in the Euclidean space. Okay. So it's the same story what I calculated for scalar, except there is a sign missing here. Okay. And so scalar was positive. So I gamma is the Lagrangian. So if I want to interpret this as the potential, then the potential is minus that thing. So I put a minus sign here. Right? The same thing which I did for scalar. Scalar, it came with a minus sign, the I gamma. So then I put it, I extracted a potential, the potential was positive. Here the potential will be negative. Potential is negative and there is 4 times. So this is the 4 degrees of freedom of Dirac fermion. Kinetic term of the scalar is also there. You can integrate it out, but it actually doesn't. So what you can do is, for instance, if you have a very heavy scalar, right? So what do we do in the standard model? Let's say we have this nu e, w, nu e, okay? We write it, we integrate out this w and we write it like that, nu e, etc. Right? So you can do it for this kind, for writing an effective theory. But there is no concept of effective potential for the fermion. Okay, this is not interpreted, this 4 fermion term is not a potential. So that's the other. So there is no interest in then doing the same exercise the other way, integrating out the scalar and leaving the fermion. Huh? It is not?
Correcting the mass,
Of what?
for the Dirac
I didn't get you.
I think he's saying that the mass is correction for the fermion can be computed in this way.
Yeah, I'm saying like if you integrate the phi and then
And I think the basic point is that there is no notion of potential for something that doesn't have a classical configuration. I think that's the reason why people do it.
I'm not curious how that, the effect of phi comes on like that will come
See, yeah, this is the effect of W here, right? If you have a scalar, it will be the same thing. You can integrate it of scalar, you will get a 4 fermion.
But I think he's here we're just integrating out to the scale, right?
Yeah.
Here it's a full inject.
Yeah.
That's, I think, is really because of effective potential.
So there is this thing of a zero, what is called a k equal to 0, this thing of a fermion background. That does not exist. A constant fermion background doesn't have a classical interpretation. So we only do it for the heavy particles in the loop. We don't do it for light particles. Okay. So let me quickly go to the thermal degrees of freedom, and I'll be very quick here. We spent a lot of. Okay, so I'll just write down quickly what happens in the standard model. Okay. So you take. So now clearly I should write the final story. So this integral is exactly the same which I did last time, right? Case in the last class, and had this 1 by epsilon which I removed by counter term. So exactly the same story. Okay. So ultimately I am getting a minus sign. Okay. So this 1 by 64 pi square m fermion 4 log of m fermion square phi minus 3 by 2. That 3 by 2 comes the same way as last time which I showed. And this guy is a function of phi. Okay. So if you want to times the effective number, so I put for each Dirac fermion I put. So normally what is counted is the top quark which has 3 colors. So there is 3 here. So 3 times 4. So it counts as 12 degrees of freedom here. So this is 3. Okay, so last is the gauge boson, and the gauge boson is vector 1, and this is plus 3 for each massive gauge boson. 64 pi square m and this constant is different. This is 5 by 6. Okay. Which I did not derive, but it's a similar derivation as your scalar. Okay. So,
25 by 6, I was looking at the Smartopedia page.
Yeah.
And I think that's coming from the V double prime phi equal to 0 condition. Because that force is m square, that is.
Yeah, V double prime.
The third one.
Third one, yeah. It comes from this condition.
So that forces the m square to be 0.
Yes.
So that's how you get the.
Yeah. So this is a different type of boundary condition. When you put, you will get a 25 by, right? 6.
25 by 6.
Yeah. Actually, I wrote it down somewhere. Actually, I have it in my notes, but anyway, I decided. Yeah. Right. Yeah. I actually have this in my. I skipped the whole.
Yeah, no, thanks.
So this is the.
Yeah, 25 by 6.
Yeah. So anyway, that was a different way of doing it, but I am now in a hurry. So I'll skip. So I am just doing it one way. Okay, now I think I'll come to the. So let me write down the full standard model story here. Gluons won't count because they're not coupling to Higgs. So the standard model story is the following, that so you have a coupling, so you will have a contribution from the H, you will contribution from the top, and W and Z. These are the particles which will couple to the lobe, and the WZ contribution is coming from the fact that you will have from the kinetic term, which is del mu minus so this is the W, this is the B, and a linear combination of this T3 component of W and B will give you photon and Z. Okay. So this is the standard model, and in terms of the physical field, then you will get a mass term, which is, so this will, if you square it, this will give me half d mu phi square plus g square upon 4 w mu plus w mu minus so this is my mass of the W mass is this one, Z mass is this one, okay, and they are phi square dependent. So in terms of a diagram, then it will look like phi and Z or W in the thing, and the contribution is this. Okay, so that's how this goes, and so just for completeness, so those are W and Z mass which you put in the Coleman-Weinberg. Okay, you have patience for a few more pages? You guys have patience for a few more pages? To be precise, 1, 2, 4 pages. Yeah? So then I'll do the thermal. And you'll see that thermal is exactly the same story. So I'll just not repeat the algebra which I've repeated for the previous steps. So here we start with the partition function. So whether it's QFT or QM, and this is trace e to the power minus beta, the operator, the Hamiltonian operator, and this is beta is 1 by temperature. And the trace is over all the states of the system that we are under consideration. So that is my partition function. And my entropy is, free energy. This is the main thing we are concerned with, is is called F. So this is 1 by T. If you take log T, you will get a beta times H. So it is this integrand. And in the field theory, when we traced out the fields and we had that integrand, we were calculating the potential, right? So this is the equivalent of potential in thermodynamics for this. So free energy is the potential in field theory. And this is also the pressure, what we have done when you write the T mu nu for a scalar field. It's the kinetic term minus the potential term. Okay? So this potential for a equilibrium system is the pressure. Where phi dot is 0, then this is the pressure. So free energy is when you have a combination of. So basically we minimize free energy. With respect to some parameter which can float, which means for instance the scalar field value, Okay, which means that if this free energy has some dependence, we calculate the dependence of the free energy for the scalar field, then what we have to minimize is this plus the potential. So this is the usual minimization of the potential. This is thermodynamic minimization of the pressure with respect to the same parameter. So this is like the thermal potential basically. We minimize this. So this is the thermal potential. Okay.
Sorry, what do we usually minimize?
We in thermodynamics, the system flows to minimize the pressure. It evolves to minimize the pressure. So it minimize this free energy is the pressure. So we minimize the free energy. So supposing this free energy was somehow dependent on the value of a scalar field, the scalar field evolved to minimize this. But we.
And what is F plus V? What is that?
So if you have a thermodynamic finite temperature system, you have this, then you have this thing coming from the loops, which I just calculated.
Okay, so those are like thermal loops.
No, so this will be a thermal loop. This will constitute a thermal loop.
And so what is V then?
So V is this Coleman one.
Oh, so the one we can calculate.
Yeah. So this is a zero temperature loop,
Okay.
and the free energy is what I will interpret as my thermal loop. Okay, and then I will minimize both together. So this will be say as a zero temperature potential and finite temperature potential. This is actually the free energy in thermodynamics. Okay. So here again I will go by the So now I have a same scalar field system. So the Lagrangian is the same of okay. And what I want to do here is in QFT. So what I will do is I will write Z as d phi, okay, of the fluctuation, okay, of e to the power minus d tau d4x L Euclidean of phi 0 to beta. So let me explain what I am doing here. First what I did, so I start with my usual partition function and take t. So I just want to do exactly t2 minus I tau. Okay. Then what happens is my LE, the Minkowski Lagrangian, which I have written there, will become minus LE, which is half d tau phi square okay, and this is actually the Hamiltonian. Okay, this is the kinetic term plus the pressure term, and so this will be the Hamilton equivalent of the Hamiltonian. So by going into Euclidean time, this usual partition function gives me the thermodynamic partition function, and this d tau 0 to beta is that beta here. Okay, so this gives me thermodynamic Euclidean phi. Okay. Beta is not 1 over T, 1 over temperature, yes. So what I did was, I went to Euclidean time, so this I times T becomes just minus tau. I removed the I, and then the range I restricted to 0 to beta instead of 0 to infinity or minus for the time. And when I went to the Euclidean space,
How is time?
so here we only have the temperature, we do not have both. For that you,
How is that? Wait, tau is some form of time.
yeah, so what I am saying is, the normal Euclidean Lagrangian, we have converted into a thermodynamic equilibrium partition function. Okay, so what I am saying that we will use the technique of this integrating out fields to calculate partition function now. So I am just, so what I am saying is, you start with your standard partition function, what is called the generating function in field theory. So this, if you have a current, you call it Zj, but normal generating function, if you make this substitution t equal to I tau and restrict the integral, that becomes the partition function, equivalent of the partition function in thermodynamics. And actually, this is just this is by analogy, but this needs a proof, like you are correctly asking. And look up Lane and Vurianian. I hope I am spelling this correctly. There is a lecture notes in this basics of field theory. So there are some few steps which will tell you how to justify that. But this I am treating as the starting point for my partition function in field theory. I will start with this and do the calculation. It's okay. Because here 0 to tau is, oh, I am sorry, this is 0 to beta. That's what you are also asking, why is tau?
That one I wrote beta in my notes.
Okay, here there is beta. Okay. So here is one more thing I have to specify, which is, I said this is true for so I am just assuming some basic things to do the calculation. So proof of those basic things I am not giving here, but please look up the thing. So here, since I restricted my time, I have to give you a boundary condition for the fields. Okay. So there are two possible boundary conditions, which is that for bosons, you will say that phi of x tau equal to 0 is phi of x tau equal to beta, and fermions phi of x is minus this. Okay, so there are so this is the boundary conditions I have for bosons, and this is the boundary conditions I have for fermions. So all these things need a proof, which I am not giving, but please look it up in the notes. Okay, so I'll just tell you how the calculations are done, and as I say, once you do the zero temperature calculation, it's a straightforward translation into this. Okay, so then if you have these kind of boundary conditions, then this will go to, okay, in Fourier space, this will go to, I will just write down the answer and you will see why, n equal to minus infinity to infinity, n belongs to integers, phi tilde, the Fourier omega n k so I should put a okay. So this is how I define my Fourier transform, and normally I would have put an integral for the time variable here, but instead of putting an integral for the time variable from minus infinity to I have done this because I want this condition to be satisfied, and that is only going to be satisfied if omega n is equal to 2 pi t times n, where n is an integer. Okay. Then you will see that this obeys that periodic boundary condition. So by putting a period, I have quantized the time variable here. This the frequency has become a quanta in n, and these are what's called the Matsubara so all you need to do a finite temperature calculation is, or not all you have to do, that when you are going from t equal to 0 to finite temperature, you have to write the fields in this omega has to be in omega n, and you take this dp0 upon 2 pi, and that you replace by t times summation n. So which gives you this. Okay. So with this translation I can do the next calculation, and my omega n here, this is true for, so this is there for bosons, and for fermions has a similar expression. So same expression where this phi is a fermion, then this n has this property, this omega n has the property, so I'll write it here. Omega n is equal to 2 pi nt for bosons and 2 pi n plus 1 t for fermion. Huh? Oh, sorry, this will be, yeah, you're right. So this will be, wait a second. Let me write this carefully. 2n plus 1 pi t. That will give you it. Okay. So 1, 3, this will be 0, 2, 4 and so on. This will be 1, 3, 5 and so on. Odd and even. Okay. So now we just let us blindly do this, or maybe we just speedily do this. So I want to calculate my effective potential by integrating out d phi, okay, of in this system. So this will give me, after I do all this, so I'll write the first step, and I go to the d cube x and l e phi, give the minus sign, and I integrate out my phi, and I have the masses here, which, so my phi has both the lambda and the usual thing, which are this will give me okay. So again I'll write it as a quadratic form with this as my, this is how I did earlier, okay, but this time it's a Euclidean here. So I get this for this just like earlier, and then I write it again as e to the where, sorry, so what has happened? I write it as exponential trace. Now in the trace, the complete set of states is now my quantized omega n and continuous k. Okay? So this, k square. Yeah, so this is k square. So omega square has become omega n, where this is not a continuously integrated over, but there is a t here. Okay. So this comes from the fact that my states are different now, it's are quantized. Okay. So the potential, then the free energy is just the exponential, this guy. Okay. So this will give me, and there is a half also. You know that there's this. So in the end, if you V beta for bosons, or let me call it V of T at finite temperature, this is going to give me T by 2, okay, n is equal to minus infinity to infinity d cube k upon log of k square plus omega n square plus m square. Okay. So the difference is that instead of integrating over dk0, d omega, I have a sum over this discrete frequency. And recognize that this inside thing is exactly the same as earlier. So now and this time it does not diverge. Actually the finite temperature regulates it, so you will see. So this is not divergent, and I will do this very quickly. Define omega square as k square plus m square. So this guy, start with, we want to calculate this n minus infinity to infinity log omega n square plus omega, right? And then we will multiply to the d cube k, etc. So, okay, I will write down the algebra very quickly and you can check it later. So then if I take a derivative, this is 2 omega n square plus omega square, okay, and this can be written as 4 upon 2 pi t. So write down omega n is in the standard form and use the fact that this is even in omega, this, okay. So this could be written as 0 to which place I had? Sorry. This was minus infinity to infinity. So I'll wait a second. I'll write. So what I have done here is I have written it as n equal to 0 term, which is this guy, and n is equal to non-zero terms, and I have used the fact that this comes as square, so that from minus infinity, so this is instead of going from minus infinity to infinity, I have taken as twice from 1 to infinity for the n non-zero terms. So that's all. Okay. And I use the identity n equal to 1 to infinity y upon y square plus n square gives you minus 1 upon 2y plus pi by 2 So use a mathematical identity and put it back there. So here y was omega beta upon 2 pi. So if I have y equal to omega beta upon 2 pi, I can use this formula. Okay, the first term I can substitute here and simplifying I get okay, and I can integrate this with respect to omega to give me 2 beta okay, so that's it. And where this omega is so go over this note slowly, you'll see. I mean, this is basic, just simple algebra, not simple algebra, just some algebra. Stick this back into this formula. Okay, here. So my one loop potential is V1 for bosons. How did I write it? So T for bosons will be d cubed k upon 2 pi cubed omega by 2 plus where omega is k square plus, and my M effective for the scalar case, as you say, is m square plus lambda by 2 pi square. So if you put this phi square in this formula, what you have is actually a effective, or now you have what I have calculated is the F, the free energy, which is equivalent of the potential, but for the thermodynamic system. Okay. So if you take this term, add that to my zero loop correction for the potential, which is the Coleman-Weinberg, together if you minimize that, okay, you will get the correct shape of the potential. So this is the thermal potential. Okay, and there is a different.
So how did you fix the, in order to go from that line you have to know the integration constant.
So what I have done is that anything which is independent of omega constant I drop. So that's like a cosmological constant or something. Anything which only involves m, which has a phi, I keep. So I dropped the. So yeah, I should actually write it here. Plus constant independent of omega. That is all of them is, each of this is effective mass. So that is effective mass calculated with respect to the classical Lagrangian. So the actual mass will be V double prime of the everything together, including the thermal mass. But that, what I am calling M effective, is the one which I got from the classical Lagrangian. Okay. So finally, if I write all of them, so I'll just write this. So this is also written as one loop finite temperature for boson. This can also be written as, you can write redefine your variable beta k equal to x, okay, and write this as 1 upon 2 pi square beta 4 beta square m square. And this thing inside the integral I am calling j beta, and it's a function of m square beta square, or m square by t square. Okay. So I just redefined it and write d cube x as dx x square 4 pi and so on. Okay, I write this in a dimensionless form. So this is, so normally what you do is you just stick in this formula for this and actually do the computation using this. That's your exact formula. But you can just try to see what it looks like at high and low temperature. Supposing I want high temperature, that means beta m smaller than 1, which means m. So temperature much larger than the mass. Then my JB is minus pi by 4. And let me write. What happened what? Good question. So this is my 0 point energy which diverges, and we can't do anything about it, we drop it. So this is 0 point energy. Yeah, you can. Yeah, that's normally what is done. That anything which is a infinity or some, it's not a denominator, it's actually a dynamical variable. I mean, would like to say something about the 0 point energy. I don't want to, brush it off as a trivial constant. It's not, it's a non-trivial constant which has to be dealt with. Okay. But in this calculation we drop it. That's all we say. Okay, so what have I written? So here is the minus, if you write m as phi times f, y times phi. Here is the minus phi cube thing that I was telling you about. So this comes from the bosonic part of the thing. I'll do the same thing, the fermionic part, so I can actually write down the. So for fermions, just write down the equivalent potential and a similar step over it. Define a V as an integral summation, which I will now not repeat. You can copy it from me later if you want. For fermions, okay, I will V one loop at finite temperature for fermions. This is 4 degrees of freedom, half times beta to the 4 times Jf, where Jf is dx. So this has a different x square log okay. So to derive the fermions, I wrote, look at the 0 temperature expression for the fermion, and instead of dk0, go to summation over odd n odd of the Mazurara, and you have a similar series of things. So these things you can look it up in lecture notes of Quiros. Very old. Finite temperature field theory. So you can look up these identities is shown. Okay. So I will stop here. Yeah, I'll. So this is how for each field, gauge boson, etc., you write the 0 temperature part, the thermal part, and then you plot look at the potential. And then you try to see that whether there is this phase transition or not. So we'll continue next time. Okay, that's all. Okay. All right. Long lecture. Do we meet little later tomorrow or 2:30? 2:30. All right.